Everyone, and welcome. Calling all ninth grade geometry students at St. Paul American School Clark, I am so thrilled to have you here today. We are jumping right into our explainer for G9, Geometry, Unit 5, Lesson 1. And the focus today? Exactly what it says on the screen. Similarity transformations and similarity criteria. You can kind of think of this explainer as your official initiation into the ranks of geometry detectives. We're going to explore how mathematicians make sense of the world, how they compare shapes, and how they solve some really big mysteries using just a few incredibly powerful foundational rules. So let's dive right in, shall we? So picture this. How do mathematicians measure a massive, towering tree without ever actually leaving the ground? I mean, you can't exactly climb up a giant redwood with a tape measure, right? Well, the good news is you don't have to. You can use your Geometry Detectives Toolkit, specifically the power of similarity. Today, our main objective is really to understand how similarity acts as that toolkit. It allows us to take small, easily measurable things right in front of us and use them to accurately calculate massive things we just can't reach. It's absolutely all about the relationships between shapes. But to really grasp similarity, we first have to understand how we create similar shapes in the first place. This happens through a similarity transformation, primarily something called a dilation. A dilation is basically a transformation that changes the size of a figure, but, and this is key, it perfectly preserves its exact shape. Think about zooming in or out on a photo on your phone. The image doesn't get all warped or distorted, right? It just scales. And what dictates that change? It's the scale factor. If your scale factor is greater than 1, you've got an enlargement. If it's somewhere between 0 and 1, it's a reduction. But the fundamental shape itself, completely untouched. Okay, let's break down the DNA of similar figures. When a shape goes through that similarity transformation we just talked about, two non-negotiable rules apply to the resulting shapes. First up, their corresponding angles will be perfectly congruent, which just means they have the exact same measure. No changes there. Second, their corresponding sides will be strictly proportional. So no, they won't be the same length, but the ratio between them will be absolutely identical across every single side. Same angles, proportional sides. That right there is the whole essence of similarity.
Now, here is the really good news. If you want to prove two triangles are similar, you do not have to go around measuring every single one of their three angles and three sides. That would just be exhausting. Instead, mathematicians have come up with three highly reliable, time-saving shortcuts. You can totally think of these as your cheat codes for triangle similarity. We're talking about the angle-angle criterion, the side-angle-side criterion, and the side-side-side criterion. Let's move forward and see how these tools actually build up your toolkit, starting with the most popular one. First up is angle-angle, or AA similarity. So the name of the game here is efficiency. The AA criterion essentially states that if just two pairs of corresponding angles in two triangles are congruent, then those triangles are automatically similar. Why just two? Well, it's because of the 180-degree rule, the triangle angle sum theorem. If you know two angles, the third one is mathematically guaranteed to be whatever's left over from 180 degrees. So if two match, the third literally has to match too. You don't even have to look at a single side length.
Next in our toolkit is side-side-side, or SSS, similarity. Now this one is basically the exact opposite of angle-angle, because here you don't need any angle measurements at all. The SSS criterion says that if all three pairs of corresponding sides between two triangles share the exact same ratio, meaning they have the exact same scale factor, then the triangles are mathematically similar. So if one triangle's sides are exactly twice as long as the others across the board, boom, they're similar. But remember, if even one single ratio is off, the whole similarity fails.
And our final shortcut is side-angle-side, or SAS similarity. This one's kind of a mix of the first two. For SAS, you need one pair of congruent angles. But, and this is a big but, it can't just be any random angle. It has to be the included angle. That just means the angle is sandwiched right in between the two corresponding adjacent sides that you're checking for proportion. If that specific sandwiched angle is congruent, and the two sides forming it share the same scale factor as the other triangle, then you've proven SAS similarity. All right, let's actually put this into practice with a real-world analysis model. Remember that towering tree from the very beginning? Let's solve that mystery. Imagine you're standing outside, and you see a vertical street pole that's 6 meters tall, casting a shadow on the ground that's 4 meters long. Right nearby, there's this massive vertical tree casting a 14-meter shadow. Assuming both the pole and the tree form perfect right angles with the flat ground, we've got two triangles here, right? One formed by the pole and its shadow,
and another formed by the tree and its shadow.
And this situation brilliantly illustrates the power of angle-angle similarity. Because the sun is just so incredibly far away, its rays hit the ground in parallel lines, which creates congruent corresponding angles right at the very tips of those shadows. Add that to the 90-degree angles at the base of both the tree and the pole, and what do you know? We have two pairs of congruent angles. By AA similarity, those triangles are completely verified to be similar. Because of that, their corresponding sides are mathematically guaranteed to be proportional. That means whatever scale factor connects the 4-meter shadow to the 14-meter shadow will also flawlessly connect our 6-meter pole to the tree's height. So we unlock the mystery of how tall the tree is without ever actually leaving the ground. Detective work established.
Before we move on, let's pause for a really quick strict misconception check. A lot of students tend to confuse SAS congruence with SAS similarity. I get it, they sound super similar, but they have very different requirements. SAS congruence requires the corresponding sides to be exactly equal in length. It basically means the triangles are identical twins, the scale factor is exactly 1. SAS similarity, on the other hand, only requires those corresponding side lengths to be proportional. They can be huge enlargements or tiny reductions. Bottom line, congruence is about being identical, similarity is just about maintaining the exact same shape. Okay, time for a quick formative check, just to see if you're tracking with me here. Take a look at the two intersecting triangles on the screen, QRS and TUS. Pay really close attention to the clues they're giving us. We've got a 35-degree angle at vertex Q and another 35-degree angle at vertex T. And notice the triangles intersect right at point S. I want you to put your geometry detective hat back on for a second. Look at the evidence. Which of our three similarity shortcuts, AA, SSS, or SAS, can we use to actually prove these two triangles are similar? Did you spot it? The verdict is AA similarity. We obviously already had our first pair of congruent angles given to us right off the bat, those 35-degree angles. But the hidden clue? It was hiding right in the center at intersection S. You see, when two lines intersect like that, they form vertical angles, and vertical angles are always perfectly congruent. So angle RSQ is congruent to angle UST. That right there gives us our second pair of angles. And because we have two pairs of congruent angles, AA similarity automatically applies. Seriously, great job if you caught that hidden clue. All right, let's do a super rapid recap of the essential concepts you've mastered today. We started with similarity transformations, specifically looking at dilations, which use a scale factor to change a figure's size while perfectly preserving its shape, its angles, and its proportions. Then, we unpacked your three reliable shortcuts for proving triangle similarity: angle-angle, side-angle-side, and side-side-side. These are the absolute non-negotiable tools in your geometry toolkit, and they allow you to bypass all those tedious measurements to prove mathematical relationships efficiently.
So we've successfully analyzed a towering tree using nothing but a simple pole and the sun's rays. But honestly, the real world is absolutely full of scales, proportions, and hidden geometry everywhere you look. From engineers 3D printing perfect scale models of rocket parts, all the way to graphic designers dilating digital images for a billboard, similarity is everywhere. So now that you're armed with these analytical shortcuts, what other real-world mysteries are you going to unlock? Keep your eyes open, 9th graders, because the world looks entirely different when you view it through the lens of a geometry detective. Thanks so much for joining me on this explainer, and keep learning.